Here, I will present AnchorSplat, a feed-forward 3D Gaussian splatting with 3D geometric priors. The core idea is very simple. Instead of growing Gaussians from image pixels, our AnchorSplat anchors them in a native 3D space, giving a compact and more view-consistent scene representation. These slides summarize the motivation. The pixel-line Gaussians are view-dependent. Different input view can produce different spots. Our AnchorSplat first defines sparse 3D anchors, and then each anchor predicts a local Gaussian. This makes the output less tied to camera views and more tied to actual scene geometry. The full pipeline has 3 modules. The anchor predictor estimates geometric priors and produces sparse 3D anchors. The Gaussian decoder projects the multi-view features to these anchors and predicts the Gaussian attributes. And then, the Gaussian refiner uses the rendering residues to correct the remaining artifacts. Importantly, the inference remains feed-forward with no percent gradient optimization. Here, the anchor predictor converts dense view evidence into sparse 3D spots. The dense depth points are first back projected to the world coordinates and then spatially downsampled. The final number of Gaussians is controlled by the number of anchors times Gaussians per anchor, rather than by the views times image resolution. The decoder predicts local Gaussians around each anchor. Image, depth, and range features are encoded, projected to visible anchors, and processed with a 3D transformer. Each anchor predicts a small local set of Gaussians. Usually we set it as 4. The center is the Gaussian, the anchor, plus a bounded offset, preserving the local geometric consistency. And then the Gaussian refiner improves the initial feed-forward prediction without retraining the decoder. It rendering the current Gaussians, compares them with the input views, extracts the multi-scale arrow features, and back projects those arrows to 3D Gaussian attributes. And then a point transformer updates all attributes of Gaussians. Here, our experiments are mainly on ScanNet++ version 2. The evaluation covers the appearance quality, geometric quality, efficiency, and scalability. This is the main quantitative results for 32 input views. Compared with any splat, our AnchorSplat improved the PSR from 20.20 to 21.48, while reducing the Gaussians from 5.5 million to 0.25 million. And also, our depth quality is much better. At the same time, the same story appears in rendered views and the Gaussian attributes. Any splat may keep floaters, ghostings, or blur regions because the representation still originates from the dense image evidence. But our AnchorSplat produced the clean 3D spot and sharper nova views, showing the benefits of anchor prediction in 3D. The final slide summarizes the AnchorSplat in 3 steps. First, this method uses geometric priors to build the sparse 3D anchors, which provides the stable scene spot in 3D space. And second, it decodes a small local set of Gaussians around each anchor, give a compact anchor-aligned representation. Third, a feed-forward refiner uses the rendering residues to further improve the geometry and appearance. So the key takeaway is simple. Moving the scene spot from pixel to 3D anchor gives a better sparse view reconstruction and fewer Gaussians and stronger cross-view consistency. And this is our poster. Thank you all.